Welcome to the 1.10 and the 1.11 notes. This is continuity and discontinuity at a point. Today we're going to talk about continuity and discontinuity at a point. To explore that, first we're going to look at discontinuity at a point. So these are things that you've already noticed and seen as we've looked at graphs, but now we're going to give formal words to them. So there's three types of main continuities. The first one is a removable discontinuity. And so here's an example of a function with a removable discontinuity. Basically, there is a hole in the graph. And then sometimes the hole in the graph has a little point above it somewhere else. So sometimes there's a hole in the graph and a point exists somewhere else, like on top of it or below it, or sometimes it doesn't. To know, like, this is what the graph looks like. I'm going to try to do some connections with equations too. And so these examples, how these would look, these are rational. How you would create this one with an equation is an irrational equation for this one. And so, for example, you would have something like this: x minus 2 times, I don't think this is the exact one, but this is just kind of a little idea. It would look like this, something like this, because if you see those x minus 2's, those would factor out, they would cancel out, so that makes it undefined. It makes it have a hole at this point, but the limits still exist. And so that's kind of an example of what that would look like. Example 2, if you were to create an equation, it would be a mix of a rational and a piecewise. So I'll show you what I mean. So you'd have something like f of x equals x minus 2 times x plus 3 for everywhere except for x doesn't equal 2, and then you would have something like 4 at x equals 2. So that's an example of that equation. I don't need you to memorize that. I just kind of want you to get used to looking at graphs and being able to kind of comprehend what could the equation maybe look like. So those are removable continuities. Basically, think hole in the graph. Then there are jump discontinuities. These are often, if you were to look at the equation, it's often a piecewise, and you'd have something like this. So it's a jump. So if you think about this, we have to, if we had our finger here, we would have to jump to get there. And so it's pretty obvious that's a jump discontinuity. Here's an example of what this equation might look like. You would have the function is 1 from when x is less than 2, and that just means like y equals 1. And then it is at 3 when x is greater than or equal to 2. So that's an example of that graph. If you were to, it's almost always a piecewise function. And then oscillating discontinuity, that is probably the most easiest to recognize, and it's like when you have something like this, when it gets really close and the discontinuity is actually at 0. And so, for example, the famous oscillating function is sine of 1 over x. If you were to plug in 0 over there, you would get error. That's not a great example of an oscillating. That's not a great sketch of one, but again, it's fairly obvious to recognize when someone's an oscillating discontinuity. And so sometimes you'll just be asked, what kind of discontinuity is this? And that would be one of your options. So we're going to look at, there's one more. There's 4 of them. Infinite discontinuity. So let's say these ones always, again, pretty easy to recognize, look something like this. So for this one, the discontinuity is at x equals 2 because it's never going to touch 2. It's just going up forever. And then here is what this graph actually is 1 minus 2 squared. The squared part on the denominator is why it goes in the same direction. And then another example here of a discontinuity. This is just another infinite discontinuity here. So again, the discontinuity is in this one is at x equals 3, and then an example of an equation would be 1 over x minus 3. So those are our 4 types of discontinuity. So you have removable, you have infinite, oscillating, and you have a jump. So we are just going to go through this first example right here and state where the function is discontinuous and the type of discontinuity. And so a guide to knowing where is it discontinuous is basically, if you were to draw this graph, where would you have to pick up your pencil? So I'm just going to start from the left, and I would have to pick up my pencil right here because there's a hole. And so my first discontinuity is x equals -3, and because there's a hole, It's a removable discontinuity. Okay, now I will continue. I'm continuing, and then we got to jump. So because I went from 4 all the way down to -3. So x equals -1, and I'm just going to write, I'm not going to write discontinuity every time. Jump discontinuity. Continuing on. Oops, sorry. We have another removable discontinuity, x equals 1. Removable. And then we have a mix here of a jump. This is oscillating right here, so I'm just going to say it's a mix of them. X equals 2 is a jump, and it's an oscillating one. And then oscillating, and then we continue on, and I don't know anything else about the graph, so we're going to assume it continues forever. So that is what it looks like from a graph standpoint. Now what we're going to work with is the definition of continuity at a point. So we just recognized discontinuities. Now one thing that we have to do is prove whether something is continuous or not at a point. So these are the guidelines, and this is pretty straightforward. Every time you do one of these problems, you have to remember these 3 steps, and then as long as you have those memorized, these problems really aren't that hard. It's kind of, they're very routine. So the definition of continuity at a point, how you can prove whether something's really continuous at a point rather than just looking at it, is it meets these 3 conditions. So function f of x is continuous at point C if the following conditions are met. The first one is f of c is defined. So it actually has a number. It has to exist. The second thing is the limit as x approaches c of f of x exists. And then finally, f of c equals the limit as x approaches c of f of x. So those 2 things have to be the same. And so what we're learning here is new, but you guys actually have been doing a lot of practice doing this and identifying this. And so hopefully we're just going to be building on knowledge you already have, and now you're just going to put it all together. So this first says, we're first going to look at the graph, and it says use the definition of continuity at a point to answer the following question. So this says, is f of x continuous at x equals -1? So if you look here, yes, it's continuous. One way to know is that I could just go through the point -1 and I wouldn't have to jump over it. So we know the answer is yes, but we have to prove it because it's saying use the definition of continuity. So we'll start with the condition f of c is defined. So this is our c value here. And so is f of c defined? So f of -1, it equals it equals 4 because there's a point, it's filled in. So yes, that part is true, it is defined. The second thing we have to think about is, does the limit exist? So as we approach -1 from the left hand, it goes to 4. As we approach from the right hand, it also goes to 4. So the limit does exist, it is 4. So we've met our first 2 conditions. Finally, our last condition is, does f of -1 equal the limit as x approaches -1 of f of x? And the answer is yes, because 4 equals 4. So the third part is pretty easy because you've already done most of the work. But because the limit and the point are the same thing, it is the same thing. And so, yes, f of x is continuous at x equals -1. And for you to be able to state that it's continuous, you have to go through all 3 of these steps. It only has to break one of those for you to say it's discontinuous, but you have to go through all 3 of the steps if it's asking, is it continuous? So here is another example, another graphical. So if we look at 2, yes, you can tell if we go to 2 right here, there's a jump discontinuity. So we know that it is not continuous. However, it's asking us to use the definition of continuity, so we must go through our 3 steps. So number 1, let's look. Does the point exist at 2? Yes, because there's a filled in spot at 2, -1. The second thing is, does the limit exist? Well, that answer is no. If you approach from the left hand of 2, you get -1. If you approach from the right hand of 2, you get 5. So the limit as x approaches 2 of f of x does not exist. Therefore, x equals 2, or sorry, therefore f of x is not continuous at x equals 2. So a good reason, so the reason, this is a jump discontinuity, the reason a function is not continuous at a jump on a deeper level is because the limits don't equal each other. So that's the big thing to know, that this is a jump discontinuity, the limit, and the reason it doesn't exist is because the limit doesn't exist. Okay, one more graphical one, and then we're going to go on to some algebraic ones. So is it continuous at -8? So our eye glance is going to say no, because we have a removable discontinuity. But again, we're going to go through our steps, and I just want you to see the connection between the graphical representation and like more of the algebraic representation. So number one, f of -8 is -3, because that's where the filled in point is. The limit as x approaches -6, or sorry, of -8. So if I approach from the left and I approach from the right, it is -6. However, f of -8 does not equal, and you're really going to want to get good at this notation because you're not going to want to write this out in words every time. But f of -8 does not equal the limit of f of x as x approaches 8 because -3 doesn't equal -6. So f of x is not continuous at -8. At x equals -8. So this one is a removable discontinuity, and the reason a removable discontinuity is not continuous on a deeper level is either because sometimes you're like not even going to have this, like you wouldn't even have this point right there. So it's either because the point doesn't exist or because the point and the limit aren't the same thing. So now we will go on to some algebraic representation. So it says, example 4 is f of x continuous at x equals 3. Why or why not? So we'll start, and I like to number these just to remember. We'll start by seeing, does f of 3 exist? So I'm just going to plug it in. 3 squared minus 8 times 3 plus 15 over 3 squared minus 9. Okay. On the top, you would get 9 minus 24 plus 15. On the bottom, you would get 9 minus 9. The numerator goes to 0. The denominator goes to 0, which means f of 3 does not exist. Because anytime you divide by 0, it doesn't exist. Therefore, you don't need to continue, because if this first condition is not met, it is not continuous. So f of x is not continuous at x equals 3. You can just stop there. You don't have to go through the other conditions if you find one that's unmet. And if you get a good hang of these, if you can automatically tell which condition is not met, you could just start at the one that's not met and then go from there. And like, you could skip steps. Okay, we're gonna go example 5. This is actually a free response, non-calculator active problem from 2011, so 12 years ago. Let the f be a function defined by f of x equals 1 minus 2 sine of x for x is less than or equal to 0, and e to the negative 4x for x is greater than 0. Show that f is continuous at x equals 0. So, big thing, we actually know that it's continuous because it's asking us to show it. So that means that all these conditions are going to be met, but we have to show that they're being met. So we're going to start by, we're concerned about 0, so I'm going to find f of 0. And I go to this piecewise function, I'm going to use this top function because it says x here is less than or equal to 0. So that's the condition that 0 fits. So I'm going to just plug that in, 1 minus 2 sine of 0. And we'll do 1 minus 2 sine of 0 is 0. So this will just equal 1. So our first condition is met. F of 0 exists. Woohoo. Our second step is we have to find the limit. Now, this is a piecewise function. So remember, if it splits at the place we want to find the limit, we have to use our equation to find the left hand and the right hand limit. So that's what we're going to do here. The limit as x approaches 0 from the left, I'm going to use the piece that is defined when the x values are smaller than 0, which again is 1 minus 2 sine of x. And so because of the first part, I already know the answer to that is 1. Now I have to find the limit as x approaches 0 from the right. And I'm going to use the piece that's defined when the x values are greater than 0, and that's e to the negative 4x. So I'm going to do e to the negative 4 times 0, which equals e to the 0 power, and anything raised to the 0 power is 1. And so the limit as x approaches 0 of f of x equals 1. So it exists. And then finally, we already know this, but we have to write it out. F of 0 equals the limit as x approaches 0 of f of x equals, which equals 1. So f is continuous at x equals 0. Okay, we have a few more practice ones. So we're going to do 2 more. We have example 6 and example 7. This one says, is f of x continuous? And this should say x equals 2. I think it says that on your paper. Is f of x continuous at x equals 2? Use the definition of continuity to explain your answer. So we're concerned about 2. So we'll start by finding f of 9. 9 is defined, f of 2. So this is the piece that tells me what f of 2 looks like, or what f of 2 is. F of 2 is 9. Now we'll work on our limits. So this will be the left-hand limit. This will be the right-hand limit, because this part is where the limit, the x values are less than 2. So I'll plug in 2 squared, and I will get out 4. And then from the right, I'll use this bottom one. I'll get negative 2 plus 3 times 2. And that gives me negative 2 plus 6, which equals 4. So the limit as x approaches 2 of f of x equals 2, and it exists. But f of 2 is 9, and the limit is 4. So f of 2 does not equal the limit as x approaches 2 of f of x, because 9 doesn't equal 4. Therefore, because that last condition is not met, f of x is not continuous at x equals 2. So we were so close, but it did not meet that last condition. I guess there wasn't really a quicker way that you could do that one, because you needed to figure out the left-hand limit, the right-hand limit, and you need to figure out the function value. So that's not really, this is an example of you kind of had to do all that work. Last one is another free response question, but this one's from 2003, so some of you, I don't think were born. But that's okay, they still reuse these problems. So let f be the function defined by f of x equals the square root of x plus 1 for 0 is less than or equal to x, which is less than or equal to 3, and 5 minus x for 3 is less than or equal to, or less than x, which is less than or equal to 5. So is f continuous at 3? Explain why or why not. So we're going to start by finding f of 3. And this is the function that is defined for when x equals 3, because that says less than or equal to 3. So I'm going to do 3 plus 1, which equals the square root of 4, which equals 2. Now I'm going to find the limit as x approaches 3 from the left. We already know, because this part is where the x values are less than 3, so we already know that's going to come out to be 2, because if I plug that into that function again, like I just did, it's going to come out to be 2. And then we need to find the limit as x approaches from the right. So I use this because these are the values where x is greater than 3. And I'll do 5 minus 3, and that equals 2. So the limit as x approaches 3 of f of x equals 2. So it exists. And then finally, f of 3 equals the limit as x approaches 3 of f of x, because they both equal 2. Therefore, f is continuous at x equals 3. And we're done. So really, you're just going through those procedures. Some problems are harder than others, but I hope it's not too bad for you guys. So, oh no. Okay, all done. Good luck.